So we're going to start or continue our chapter 3 with looking at three main kinematics equations. These kinematics equations only work if we know that we have constant acceleration. Okay, and all the problems that we do with our kinematics equations will have constant acceleration, but you can't use the equations unless we know that for sure. So we can't have things speeding up and slowing down in the same motion. We have to solve those parts separately. Okay, we need to have constant acceleration in order for these equations to work. Okay, so I'll refer to these three equations as your kinematics equations often. So you'll get so good at using these that they'll be memorized, but you will have the opportunity to write them down on an equation sheet. So I'm going to hand out or let you have an equation sheet if you want one. But for right now, go ahead and get this equation written down in both your notes and on your equation sheet. Okay, first and foremost, V sub f, what do we think that means? Final velocity, good. And what's our units for velocity? Final velocity units are in meters per second. Okay, what about V sub I? Initial velocity. Also in meters per second. What's A mean? Acceleration, good. And what's our units for acceleration? Good, meters per second squared. And finally, T is time. Okay, and it's in just seconds. Okay, in order for these equations to work, our units have to be these 4 units. Okay, they have to be these 4 units. Okay, before we could get away with things in kilometers per hour and time in hours, we can't do that anymore. So it has to be meters per second, and time has to be in seconds. Okay? Questions on this equation so far? All right, let's try some problems that go with it. A bus is traveling at 30 kilometers per hour, speeds up at a constant rate of 3.5 meters per second squared. What velocity is it at 6.8 seconds later? Okay, so we're going to go ahead and start solving some problems here. I'll give you a couple minutes to get it written down if you want. Otherwise, you can start making your list of variables you know. First and foremost, we want to start looking at the numbers given to us in our problem. So 30 kilometers per hour tells us what? What variable does that tell us? Initial velocity, good. So V sub I is 30 kilometers per hour. Does that work for us? No, we need to get it to meters per second. So we can use our shortcut here, right? Times 0.2778. Need to have your calculator out if you don't already. Okay, so I had an initial velocity of 8.33 meters per second. So I'm done with that number now. What does my 3.5 meters per second squared tell me? Acceleration. Okay, even if you don't get the lingo that it says it speeds up, we should be able to tell by the units itself that that's acceleration. Okay, because the units for acceleration are meters per second squared. Speeding up should tell us there's a change in velocity, which also indicates acceleration, but we should be able to tell by the units alone. Okay, and we know that 6.8 seconds is time. What variable are we solving for? Yep, V sub f, or final velocity. Okay, very good. So let's think about this for just a second. If we know that our initial velocity is positive, And we know that our object is speeding up. What about the sign of our acceleration? What should the sign of our acceleration be? Positive. They should match, right? Whenever something's speeding up, our velocity and our acceleration should match units. All right, so let's solve for final velocity here. We'll use v sub f equals v sub I plus at. V sub f is what we're solving for. We'll plug in our variables. And I got a final velocity of 32.13 meters per second. Equation. Okay. D sub f equals d sub I plus VIT. Realistically, this t sub f means final time. We really don't need to include that subscript f on time. Okay, because essentially they're going to give us a time starting from point 0. So we don't really need to have that f in there, but your book puts it in there, so I did. Okay, plus 1/2 at squared. Same with this sub f. You don't really need to include that subscript, since our initial starting time is always what? 0. Yeah. Okay. So this equation can go in your notes and on your equation sheet. We're going to talk through our variables here one more time. Okay, tell me what d sub f stands for. Final what? Final distance or displacement? Yep. Final displacement. And the reason that we have to make sure to include displacement is because d sub f can be negative. We can have a sign there. Okay? What d sub f is really our final displacement or our final position. You can think of it like that, final position. How far we are from where we started. We could be above where we started. We could be below where we started, to the left or to the right. That d sub f could have a sign that goes with it. It could be both positive or negative. And the thing we know about distance is that it can never be negative because it's a scalar. Okay? So this you have to think of as either displacement or position because you have to be in a certain location from where we started. Okay? Whether it's behind, in front of, above, below, things like that. Okay? What about d sub I? Initial displacement. Or you can think of d sub I as our starting position. Most of the time, d sub I is going to be set to what? 0. Most of the time, d sub I will be 0 meters.
Please excuse this interruption. Any student wishing to retake their pictures can report to the bingo room at this time. Any students needing to retake pictures can report to the bingo room at this time. Thank you.
Okay. All right, we know what v sub I is. We know what t. We can leave this f off, really, so it's just time. We can leave f off there because it's time. But we know what v sub I is what? Initial velocity, good. Time is in seconds. A is acceleration, and time is also in seconds. The units for displacement, d sub f and d sub I, are both just meters. Okay, they both need to be in meters. Telling us how far we ended up from where we started, things like that. Or, in essence, our starting position for d sub I. Okay. More often than not, we'll set d sub I equal to 0 because we'll choose the origin to be where our motion starts from. Okay. So let's go ahead and try one here. Train accelerates from rest at a constant rate of 3.15 meters per second squared for 1.57 minutes. How far does it travel in this time? Tell me which variable this equation is missing that we've looked at so far. It's missing what variable? It's missing time? It's missing which velocity? It's missing final velocity. So this equation we can solve even if we don't have final velocity given to us in our problem. Okay? So we have a way to solve for that. Okay, this tells us it starts from rest, which means v sub I is equal to 0. Our initial velocity is 0 if it starts from rest. Our acceleration is 3.15 meters per second squared. Our time is 1.57 minutes. What should be the red flag that's jumping out at you here? Time is in minutes. So we need to multiply that by 60 to get it in seconds. Okay. So we've got our velocity, we've got acceleration, we've got time. What variable here are we solving for? Tell me what variable we're solving for. We're solving for final velocity? Final displacement, because it asks how far. Not what speed is it, or what velocity, how far. So that's distance final. Is going to be our question mark. What's our initial position here? What's d sub I? 0. Okay, if it doesn't tell you, if it doesn't give you a specific starting position, we assume that it's 0, because we're starting to look at this problem basically from point A, which is our starting point, to a certain time later. So we're trying to find out how far it traveled during that time, how far it ended up from where we started. Okay, so we can go ahead and plug in here. D sub F equals 0 plus 0 times 94.2 plus 1/2 3.15 times 94.2 squared. It's really, really important for you to understand that only time is squared here. Only time. Not that whole term, only time is squared. Okay, so if you need to put the little square inside the parentheses like I did to remind yourself of that, that's fine. Okay, but only time is squared. I am sure that some of you will square that whole term, even though I'm saying it in class 5 times. You have to remember that only t is squared. Okay? And when our initial velocity is 0, this term can essentially be dropped also, because 0 times any number is 0. So we don't need. Does that look better? Okay. Okay, for problems like this, you can round that up to a whole number. I'm not really concerned about significant figures here. I'm more concerned with whether or not you can do the math correctly. So here, answers can vary just a little bit depending on rounding, but for the most part, they should be pretty similar. Okay, in an emergency, a driver brings a car to a full stop in 4 seconds. The car is initially traveling at a speed of 25.4 meters per second when the braking begins. What's the car's acceleration? How far does it travel before coming to a complete stop? Okay, so if you want to get this written down, that's fine. I'll give you a couple minutes, and then we'll start picking out our variables here. All right, let's go ahead and start picking out some variables here. It says a driver brings a car to a full stop. What variable does that tell us? The car comes to a complete stop. final velocity. Final velocity, and what does that mean? Final velocity must equal 0. Good. Okay, because it's coming to a complete stop. They told us our time is 4 seconds. And they told us our initial velocity, 25.24 meters per second. Okay, does anyone not see where we came up with those 3 variables? Okay. This asks us, what's the car's acceleration? What equation can we use now to solve for acceleration? We can use our very first one, right? VF equals VI plus AT. None of the kinematics equations we use can be done without acceleration. So if it would have just straight asked you how far does it travel before coming to a complete stop, we'd have to recognize there that we don't have our acceleration. We've got to find some way to solve for it first. Okay, so we've got to have acceleration for all of these types of problems. So let's go ahead and solve for that first. 0 equal to 25.24 plus A times 4. When we solve for this variable, we're going to subtract 25.24 to the other side first, which gives us negative 25.24 equals 4a. And gives us an acceleration of negative 6.31 meters per second squared. We've got our acceleration to be negative 6.31 meters per second. We want to find how far it travels, which means we're solving for which variable? D sub f. What do we know about d sub I? It's 0. Okay, it doesn't give us a starting location, which means we're going to assume that d sub I, or our initial displacement, is 0. So d sub f equals 0 plus, this time we have an initial velocity, so we can't leave that as 0. 25.24 times time. I'm going to run out of room here. We plug in the acceleration that we solved for, and we square only our time unit. Okay, so I got my final displacement to equal 50.5 meters. Okay, so this is our final kinematics equation. Vf squared equals Vi squared plus 2a delta d. Remember, anything that's final minus initial is essentially the same as having a delta, right, or change in. You can write it however you feel more comfortable with. All right, we don't have any new variables here, right? All of these we've seen before. Which variable are we missing here? Time. Good. So this equation we can use if we don't have time, if we're not given time. We can use this equation. Okay, so for all of our kinematics equations, we have to have initial velocity and we have to have acceleration. Those are two things that we must have. But there's equations that we can use if we don't have final velocity or if we don't have time. All right. Most of the time, what's d sub I going to be set to? 0. So more often than not, it'll just be 2a times final displacement. But we still need to be aware that it's really final minus initial here, okay, or change in. All right. Car starts at rest and speeds up at 3.5 meters per second squared after the traffic light turns green. How far will it have gone when it is traveling 25 meters per second? Okay, so by telling us it starts at rest, what variable does that give us? What variable? Initial velocity and initial displacement. They both can be, both of those variables can be understood that they're zero. The specific words start at rest tell us velocity is equal to 0. But since it doesn't give us a starting position, we assume that d sub I is 0 also. Okay? What about this number right here? What's that tell us? Acceleration. And how do we know it's acceleration? Meters per second squared. Our unit only must be able to tell us what that is. Okay? What about this variable, or I'm sorry, about this number right here is when it's traveling at 25 meters per second? Final velocity, very good. Okay, and it asks us how far will it have gone, which means we're solving for final displacement. Okay. Since our final velocity is positive, what direction does that mean we must be traveling in? The positive direction or the negative direction? We must be traveling in the positive direction if our final velocity is positive. If our final velocity had been negative and we started from rest, that means we must have been moving in the negative direction. Okay? So we're going in the positive direction here. Let's go ahead and solve here for displacement or final displacement. V sub f equals 25 squared equals 0 squared plus 2 times 3.5 distance final minus 0. Okay? For these problems, I'm giving you the hint by telling you what equation we're going to use. Okay? Once you start working on these problems on your own, you have to be able to identify that I'm missing my time variable, which means I can either solve for time and use another equation, or I can understand that this doesn't need time and I should use this equation. Okay, so you will have to start picking out which equation to use based on the variables you have given. Okay, but for right now, we're working with each of them individually, so we're not doing that. Okay, so you're going to take 25 squared, which is 625, equals 7 df. Right, if it's minus 0, we can drop that second part of the term, so 625 divided by 7. Did we get a final displacement of 89.3 meters? Yeah? Good. Or a displacement of 125 meters, how long does it take to achieve this speed? Okay, a car accelerates at a constant rate of 15 meters per second, from 15 meters per second to 25. So that means we know our initial velocity is equal to what? 15. Good. And we know our final velocity is equal to 25. It travels a distance of 125 meters. Is this distance initial or distance final? I'm sorry, say that one more time. Final. Thank you, final. Okay. What about our initial displacement? 0. Right? Doesn't give us a starting position. So we can assume that our starting position is 0. And tell me what variable the question is asking us to solve for here. That's what it's asking us to solve for?
Time.
It's asking us to solve for time. But can we do any of those things if we don't have acceleration? No. So the reason we want to use this equation is to solve for acceleration first. We don't have acceleration or time. So we've got to solve for acceleration first before we can take that next step to solve for time. Okay? Does that part make sense? All right, so let's solve for acceleration first. VF squared equals VI squared plus 2A, 125. And we could say 125 minus 0, but that doesn't do us a whole lot of good. You can leave it in there if you want. You don't have to, okay, but you can. So I'm going to take 25 squared minus 15 squared because I'm going to move that to the other side. And I get left with 400 equals 2A times 125, which is 400 equals 250A. And I get my acceleration to equal 1.6 meters per second squared. Okay, the 400 comes from taking 25 squared, which is 625, minus 15 squared, which is 225. Okay, that's where the 400 came from. So I just took out one little step there. So now which equation can we use to solve for time? The first one, yeah, use the simple one. Use the easy one. So we'll use VF equals VI plus AT to solve for time. Our velocity final is 25. Velocity initial is 15. 1.6 times time. These types of problems, you can write these down. You don't have to, but these are the process. This is the process that we should go through as we start looking to solve these kinematics problems. First and foremost, read the entire problem. Don't assume you know what it's going to ask. Okay, just don't. Just read the whole problem. See what variables you have, what you don't have, and you can dictate which equation, what variables you have to solve for based on that. If you can draw a diagram of the motion. Once we start getting into vertical motion, drawing a diagram will be much more important. For our horizontal kinematics, it's not quite as important because things move very simply from point A to point B. Okay, once we start dealing with kinematics in the vertical direction, things that could go straight up and come straight down, things like that, we're going to need the diagram a little bit more. Until that point, the diagram is not super important for horizontal kinematics. Okay. Right, what you know, that's putting those list of our variables in the margin. Consider what equation we should use, see what you have, see what you don't have, which equation matches those things. Calculate, and then check to make sure that your answer is reasonable. Does it have the correct units? Okay, so here if you give me a variable without units, it'll be incorrect. You have to give me those units that go with it, okay? All right, let's try a couple now where you get to pick the variables, you get to pick the equation, and we'll see if we can do it, okay? Car starts from rest and accelerates uniformly for a time of 5.21 seconds for a distance of 110 meters. Calculate the acceleration of the car. When it tells us it accelerates uniformly, all that's telling us is that it has constant acceleration over that time, which means we can use our kinematics equations, okay, because we have to have constant acceleration. All right, so I'm gonna have you give me my covered. Okay. Angel, tell me find one variable for me.
Time is 5.21 seconds.
Okay, good. Aiden, find one for me.
Is 110 meters displacement final?
Yep, very good, very good. Okay. Initial displacement is 0 because it doesn't give us a starting point, just tells us how far we've gone. Jordan, give me one. We have one more here I think we can find.
Initial velocity is 0.
Very good. Initial velocity is 0. The reason it's 0 is because it starts from rest. That's where we get our initial velocity equals 0, because it says it starts from rest. Okay, and our question mark variable here is acceleration. That's what we're solving for here. Okay, so let's take a look at our equations. First of all, let's take a look at what we have and which equation we can use to solve for that. The first, second, or the third. What do we think? The second equation, df equals d sub I plus vit plus 1/2 at squared. Why do we think we have to use that equation? You're right. It has everything we have, and it's missing one variable that we're missing, which is? Well, okay, yeah. It has acceleration, which we're solving for, but it doesn't have final velocity, and we don't have final velocity. Okay, so that's the reason we can't use equations number 1 or 3, because we don't have final velocity. All right, so let's plug here and try and find acceleration. Distance final is 110. 0 plus 0 plus 1/2 a 5.21 squared. Okay, so why can I make this whole term 0 right here? Exactly. This is initial velocity times time. That's this term right here. If initial velocity is 0, time times 0 would be 0. Okay, so anytime our initial velocity is 0, we can just basically drop that term. Our distance initial or displacement initial is 0 also. Okay, so we're going to take 5.21 squared times 0.5. And that gives us 110 equals 13.6a. And that gives me an acceleration of positive 8.1 meters per second squared. All the way on your own. Okay, so I'm going to give you about 5 or 6 minutes, and then we're going to see if we match answers. Okay, please raise your hand if you have questions or ask some person sitting next to you, but I want you to try this one on your own. All right, so up on the board I put my math for this. There's 2 different ways that you can solve for displacement once you found your acceleration. Do we agree at least with the acceleration number here? 11.2? So once you solved for acceleration, there's 2 different ways you can go about solving for final displacement. How many of you use this way right here? df equals d sub I? Good. Did anyone use this way? Yeah, it doesn't matter. Either way, it gives us a little bit of variance in our answers, but for the most part, they're generally the same. Okay? Yeah. Last practice problem. You can do it. Okay? This one's a little bit trickier, so we're going to talk through this one together, and I'm going to let you solve it by yourself. So we're designing an airport for a small plane that must reach a speed of 27.8 meters per second before takeoff. The plane accelerates at 2 meters per second squared. If the runway is 150 meters long, can this airplane reach the proper speed to take off? So let's think overall about what this question is asking us for. First and foremost, we need to picture the motion of the airplane traveling down the runway. When we say takeoff speed, we mean the speed that it's just leaving the ground, okay? So when a plane begins its path on the runway, what's its initial velocity? 0. Good. So our initial velocity here would be 0. So we're only looking at the portion of this plane from when it starts its engine, basically, to the point it's just about to take off. We're looking only at the runway portion of this plane, okay? It has to reach a speed of 27.8 meters per second. So that means its final velocity must be 27.8 meters per second. Oops, not squared. Okay, it accelerates at 2 meters per second, so we know its acceleration. We don't know time, which is not a huge deal because we have an equation that we can use without time. So it tells us the runway is 150 meters long, but it wants to know basically, will the plane reach a high enough speed in that distance in order to take off? Okay, so this question means we need to work backwards a little bit. We need to find out the exact length that the runway needs to be in order for that plane to reach a speed of 27.8 meters per second. So the 150 meters here is just a reference point for us. We've got to find the distance it takes for this plane to reach that final speed of 27.8 meters per second. Okay, and then we're going to be able to compare, is 150 meters long enough or is it not? Okay, so we're going to solve here for d sub f. Okay, because it's asking us, can the airplane reach the proper speed to take off within that given amount of distance? So tell me which equation we should be using here. The third one, vf squared equals vi squared plus 2a delta t. Okay, our final velocity we know is 27.8. We're going to solve for distance final or displacement final. We want to see how much distance or how many meters do we need in order for this plane to take off at the right speed. Okay? Do we agree here with our final displacement?